broadcast.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody, and thank you for joining us for today's webinar looking at Artful air distribution, balancing form and function. We have about an hour-long event for you today, and Price Industries is a registered provider with the American Institute of Architects Continuing Education Program, which allows us to offer you one AIA credit for participating in today's event. At the conclusion of the webinar, we'll send you an email with a link to a short form that you need to complete in order to request that credit. Our presenter today is Jerry Sipes. He's the VP of Engineering here at Price Industries. He has extensive experience in the air distribution industry and serves at a national level with a number of committees that advance the use of high-performing air distribution. And Jerry has been very privileged during his career to work with a number of architects and engineers on a broad spectrum of air distribution product applications and technologies. So with that, I will pass the presentation over to Jerry.
Hello. So in this presentation, the idea is that we want to discuss ways that the fundamental air distribution is incorporated in a building, and we're trying to talk about both the aesthetic, the functional, and a little bit as to what the occupant's perception is of these devices. So the three learning objectives that we have is first, understand the way these units can be customized, but also there's going to be a very brief discussion on how they actually work, because we have different ways of distributing air. And then, of course, we'll try to get some sort of a weight as to how you can influence as a designer what these end users' products look like. And then we'll also try to, at the time it's appropriate, to discuss how the different members of the team in particular as a manufacturer, how we can help you with some of the complexities of these designs. Now, the first thing that I often consider, and I tell all my engineers, that we have to consider what the end use is. You know, the owner's goals, their functional requirements. Is air quality a fundamental component? And I personally believe it should always be part of every building. And the other three things I think that are really relevant are how much energy will we use over the life cycle of this building to do this conditioning. And energy is a major topic in most of the places in the United States now. Recently found out that for air conditioning, the United States uses twice as much as the rest of the world does for thermally cooling buildings. So this is a major topic that will get worse as time goes by in terms of stringency. Noise is always a fundamental component, and depending upon the occupancy, it can be really, really important, say it's a production center or a theater, or it could be a factory where noise is not as major of a consideration. So there's some diversity. And you know, it's interesting, when I left college, I found out an interesting aspect of the world. I was trained, as most engineers are, that life cycle cost is how you make decisions, but first costs are heavily weighted. And so it's interesting, if I can, I will try to tie these different technologies in terms of cost relevance to the most common basic form that we use, overhead mixing. Because I do believe that life cycle has an important part of the building. It's all about balancing form and function. Oftentimes, we end up focusing on one of these components, and the reality is it's always a blend thereof. And if I look at the different technologies that we'll discuss, chill beams, for instance, versus displacement, we have a mixing system compared to a stratified system, and they have a different weight in terms of comfort, air quality, energy consumption, and so forth. And based on their placement inside the building, they have a different impact on the aesthetic. Are they at the eye level, are they above the eye level, or are they hidden in plain sight? And so we'll discuss these components as we go through this presentation. So let's say that we've made a selection in terms of the type of air distribution we're going to utilize. Let's say it's displacement. stratified. So once I've decided on the type, I would then decide where to place it in the building. And there's a degree of flexibility associated with this. But also, there's a degree of flexibility associated with the color and what the face of this product looks like. Perhaps the shape is the way we blend it inside the architecture in a way that it's not as blatant or obvious, but more part of the interior finish. And in my mind, by the time we're done with all of these various factors, what we're talking about is how integrated the air movement, ventilation, and thermal conditioning of the building is with the interior design. So the first technology that I will briefly discuss is radiant. And the radiant that I'm going to talk about is based on water heat transfer. This is not based on electrical reheat radiant components. But even if it were, the fundamental component of radiant heat is that it is heat transfer without a media. It's all electromagnetic, so it's all line of sight. And radiant is a very big part of our buildings, but it's not often considered as important as it's become in the last couple of years because of the amount of sunlight we're putting inside our buildings is taking some of the solar heat and moving it further in than we did 20 years ago. And the occupants' perspective is that they have all these different sources of heat, be it the window, be it the wall, the floor, other objects. They all interact. And as long as the occupant isn't aware of one being a strong source or sink, if you will, if it's cooling, then we can achieve thermal comfort. It's when we start getting these radical asymmetries that we start having issues. Common one is the western side of a building in the afternoon. If you're in full sunlight, the temperature of the space could actually be ideal, 75 say, but the occupant might perceive it to be 90, and something that will generate thermal complaints. So this is something that I try to discuss with a lot of designers in an effort to understand and potentially control it. Now, one of the real reasons that water systems have come to the forefront, besides being a more efficient media for transferring energy in and out of the building, is that the physical size of the elements to do this energy transport are much, much smaller than all air systems. For instance, and the energy that I could take to cool or heat a building in an 18 by 18 duct could easily be handled by a half-inch pipe. And this is due to the water's larger capability of absorbing or holding heat in it per given unit of volume compared to air. Now, there's still a ventilation requirement, so roughly a 7-inch diameter duct would handle the typical ventilation requirements of an office space an 18 by 18 duct would service. So if you're looking at it from a new building's perspective, putting a water system in means my interstitial space can be vastly reduced. You might be able to raise your ceiling inside the space, given a perception of larger volume. You might be able to potentially lower floor heights. Or if you're doing a renovation of an existing historical building, for instance, often interstitial spaces are considered a challenge, and it's easier to put in these smaller systems. One key note, though, that when I normally give recommendation, if I'm cooling with water systems, the water, either hot or cold, is simply to handle as much of the sensible or dry load in the occupied space as possible, and then I would try to do all humidity control or latent energy removal with the volume of supplier I have inside the space. And the idea behind this is that I minimize my risk of condensate if I'm using this for cooling, which is a common concern. And also I've optimized my building's energy consumption in terms of how much it takes to transfer the amount of cooling or heating to the space, water being the more efficient media. Now, water, of course, requires a ventilation system. So we typically see displacement ventilation used a great deal, or overhead mixing for that matter. Active beams being a water system that actually is a mixing system at the same time on the air side, and sometimes natural ventilation. So I'm going to go into more detail on the displacement, the mixing systems, and the beams, and I'm going to sidestep the natural ventilation due to lack of time. If you were interested in any of these topics that I'm going to discuss from this point forward, there are webinars that are on our website under the Media Center that address a lot of the fundamental components on how they operate or how you might fit it in specific constructions such as laboratory spaces that will be beyond the scope of this time we have today. In terms of flexibility for radiant systems, one of the bigger challenges to me is that when we're cooling with them, or heating for that matter, even though we could put in really cold water or really hot water to drive the energy exchange between these radiant panels and the occupancy, we can't really go beyond a certain level of differential, because the occupant, if it, say it's hot water, they would have a hot head, and they would call and complain about having a hot head. People are very sensitive at the head level, so we have a difference in temperature that we can't exceed before we start getting thermal complaints. On the cooling side, we don't even come close to approaching the limit for thermal complaint, because we hit the dew point of the room, and we don't want water to condense on these surfaces, so we don't have the water supply going to the panels to go below dew point. And control systems and such for that are discussed in those other webinars I mentioned. So that means that to get the heat transfer, to maximize the sensible loading that I can handle with these panels, I must have a large number of them inside the space. So that's why size is considered a not as flexible component of the selection process. Now, in terms of what they look like, their location, their shape, whether they're embedded in the materials of the wall or floor or ceiling, or if they're exposed, mounted on the wall, ceiling, wherever they need to be, those are very flexible. So the most flexible item, of course, is what color are they. Now let's just take a look at a couple of buildings with radiant products in it. This is Telespark New Science Center. Now, this building was optimized for energy savings and also thermal comfort. The radiant panels, you see your pods in the ceiling plane, and they have this grid pattern of perforated holes in them. Now, these holes provide two purposes. They give you an aesthetic look that's different than just a flat surface, but also radiant panels, if they're completely metal surface, they reflect sound very effectively. And unfortunately, that would raise the amount of background sound inside the space. It might even sound like it's echoing. So we oftentimes have a perforated face with the sound-absorbing media on the back of it, so that it tends to absorb sound rather than to reflect it. Now, some of the things that was interesting in the way they put these products in is you notice that on the top right-hand side, that radiant panel actually has been cut out in such a way that it fits to that concrete structure, but still you get the overall grid pattern of layout that we had in the ceiling plan. Now, when this was selected, they also put in displacement ventilation as the media for providing ventilation air to the space and some cooling. They achieved a 44% energy savings compared to what their base model said it would be. And we helped them with the face selection, how we fit in the architecture, and so forth. Cooper Union is another radiant panel product. Now, this is actually an activated metallic ceiling, where we would activate the metallic ceiling through attaching radiant tubing to the back of these panels. And this also was interesting in that it included integrated services. So you can see in the ceiling that through the center part of this space, we have the air distribution component. So this is a continual straight line. And then we have in this median the fire sprinklers, lighting, and speakers. So when we start talking about this, this is integrated in the way that it was incorporated in the ceiling plane. And there's been some discussion that this might actually be a benefit to the design as it goes together in construction more effectively or efficiently than it does in the traditional construction cycle. Now, there is a webinar that will be coming up talking about integrated services in particular that will be announced at the end of this presentation. If you're interested in this topic, it would be a great one to follow. So leaving chill beams and leaving radiant panels and going to another water-based heat transfer product is beams. Now, chill beams come in two varieties. They come in an active, which incorporates the supply air to the room, the ventilation air often, and then we have passive. So I'm going to first describe very briefly active beams, and again refer you to our library of webinars if you want more in-depth on how this product is selected and operated. But in essence is an active beam could be considered an induction terminal unit. What it does is take your primary air, your ventilation air, could be cool or hot or neutral temperature. And it takes this air into this plenum, and the static pressure of this air in the plenum drives that air through a row of nozzles. In this case, there's a two-way discharge, so there's two rows of nozzles. And this takes the static pressure and converts it to velocity pressure, and what we have is this very fast discharge out of these nozzles. This, in turn, causes a low pressure center to form here above the coil, and then draw room air up through the coil, mixing it with the supply air and entering the room as a mixed media of recirculated air and primary air inside the space. And this is an incredibly effective way of taking localized recirculation and achieving a high level of sensible heat transfer inside the space, both heating and cooling. Again, for more information on this topic, I would refer you to one of our webinars. On passive beams, a passive beam is very similar to the active in that it uses a water coil for the heat transfer of sensible cooling or heating inside the space. But it doesn't incorporate any primary air to do any room air movement. What it does instead is rely on gravity to do this movement for you. So in terms of energy density, a passive beam is roughly a fifth in that ballpark of the capacity per lineal foot of beam that an active beam has. But it's very, very, very quiet. What we have this do is we put it over, say, a heat source, or let's say it's over a window on the exterior wall, and any hot air rising off that window in the summer months would come in contact with the fins of this cooled coil. The air becomes slightly denser, and through gravity would then tend to fall toward the floor, and this induces room air through the coil. And you get a very effective heat transfer for minimal energy expenditure in terms of moving heat transfer in and out of the building. This is often used as supplements to displacement systems and active beams. In terms of flexibility, the shape is fairly fixed. I mean, there are at least 15 different models that our company supplies, but they are finally based on a water coil. And so water coils are typically rectangular. Hence, the shape is not considered a major flexible design aspect. Now, what it looks like or where it's located and the size of it are to a great deal flexible, but its location and its color, again, are very, very flexible. These products can be installed in the ceiling plane. They can be installed below the ceiling. They can be installed above a perforated metal ceiling. They can be installed in a soffit, sidewall, vertical discharge, or horizontal discharge. They can be installed level with the surface of the floor. Flexibility with the chill beam is an amazing degree. Let's just look at a couple of buildings with them. The Audi Museum comes to mind. Now, this is a building in Germany that is a very passive system. It uses passive beams. They're installed above the perforated metal ceiling that you see on the left and on the right. Displacement ventilation is used. It wraps the columns and is at low level on the floor. The curved linear that you see on the right-hand side is actually the return for the supply air inside the space. A very calm, quiet, peaceful, well-ventilated space. Another place that we've looked at beams in is Borndale Elementary. Now, it's interesting to start seeing this trend where I start talking about beams or panels, and we start talking about displacement ventilation, often used in conjunction with it, because when we start talking energy savings, it comes to the forefront. Borndale originally started as unit ventilators in its design process in the classrooms, and unit ventilators, for better or worse, are often a little louder than what acceptable designs would now allow. And so we showed that you could put displacement in, and while we were going through this, we went through and talked about beams, and they put them in the common areas, and I think it's a really cool aesthetic look. In the ceiling cavity here, you see one-way beams from the sides of this common area blowing inward amongst the lights. So it's more of an architectural feature, and yet we also achieved a high level of thermal comfort inside the space for minimal to any additional cost compared to the original design intent. Now, this is one of Gensler's offices. This was it is a conference room that they have. Now, there were some serious issues and concerns on our side. We have beams along the perimeter of this space, and they're all one-way blowing inward. And you see that there is no ceiling. So one common problem you might run into in an exposed space like that is if the air doesn't have a surface to flow along, it might start migrating downward toward the occupants. And the worst thing you can do is hit an occupant in the head. They'll notice that air volume around their body, unless the velocity is lower than around 50 feet per minute. The other thing is we had to worry about with the light. So we can't have it move. And to make this happen, we did a mock-up. We looked at some CFD work. And then to improve the condition of the appearance, we also made it look more like a continuous product. Ogden High School. This was both a renovation of an existing 1930s building and an addition onto the cafeteria area. And we incorporated chilled beams inside the ceiling space here. It has received a lot of positive comments back from the end users in this case. And I think you can see that we were able to hide a lot of the surfaces above the cloud ceilings. So it's an interesting structure. One area that I think we have a lot of opportunity in is soffit mounted products. Oftentimes we're trying to, let's say, blow air across an atrium to wash an exterior wall surface, and we need a long distance of throw. This is actually a localized recirculation unit that does that exact thing. The return air is drawn in the bottom of this beam through, in this case, a floating bar linear, which means you can remove it easily to access it for maintenance should you need any. And you see this discharge coming out now. This discharge opening can be either a linear slot, a linear bar, a sidewall grill, a louver face, or no face whatsoever. So it can also be oriented horizontally in this case, or vertically in another case, and has been used for years. So this is a neat option. Now, chilled sails. You may or may not have heard of chilled sails. Sails are a hybrid, if you will, in my mind, between a flat panel and a chilled beam, a passive beam. Whereas a passive beam has a convective cooling and a radiant panel has a radiant cooling effect or heating. In the sails, you have a large space area of this airfoil that gives me radiant heat transfer, both heating and cooling. But you also have the ability for the air that's stratified or warmer than these airfoils to become in contact, become slightly cooler, slightly denser, start migrating toward the floor. So what you get is a higher capacity out of this with very low velocity and a great deal of thermal comfort, because I can handle more of my sensible load with this product with less surface area than I can with, say, a radiant panel. And because of the breaks between the airfoils, I can actually have absorptive material above them and also mitigate sound. In terms of flexibility, they're somewhat limited in what the face looks like, the size, shape, location. You can, however, have them exposed above the ceiling, hidden, or below the ceiling, or flush to the surface. That's really its major flexibility. Of course, color is on that list. Now, this is my conference room, and I have to admit I'm quite proud of this room because I've been playing with the functionality of this room. But the original reason that I put sails in this room came from thermal complaints from our own people. We had, this room was designed originally with this odd shape in the ceiling with that curved linear around it as a way to highlight the fact that we could curve these linears. We also had 1,000 CFM air going inside this space to cool it, and a direct south-facing windows, and we had a lot of radiant problems inside this space. So what I did was I dropped the air volume down to 100 CFM, which is the minimum for ventilation purposes, and then handled all the latent load with that air and all the sensible load with the water system through those sails. And it's gone from being a almost never used room to being one of our most commonly requested conference rooms, simply for one reason. It is always the exact same temperature year-round inside this space. So that I think is a very interesting product. Now, there's also been use of this in industrial spaces and commercial spaces. This is another view of a different aspect of the Gensler office, where they have sails. Now, these sails are flush with the perforated metal ceiling you see. They were customized in length and also set up so they had certain discrete steps. They look like they're continual runs. To make this happen for ventilation purposes, underfloor air was utilized. One building that fascinated me was the Upper Iowa University Liberal Arts Building. This was something I talked about at ASHRAE summer of last year, gave a presentation on it. This this was an energy consumption reduction of 67% compared to an overhead mixing system. Now the building did achieve LEED Silver. It potentially could have gotten more. I'm not certain what the math was, but with 67% energy reduction compared to overhead mixing, that's phenomenal. It's really too bad we can't do that everywhere. I live in Atlanta. My humidity levels alone would say, hey, no, wait, sorry. Because what they did was they used ground source heat pumps as part of the system to provide the cooling media, heating for the water, and then 100% outside air. If you have a conducive environment like where this building is located, you can do that. Now, one thing that they wanted to achieve was reduced structure, and you can see that the structural beams are actually in drywall running through the center. And then the sails are close coupled to the acoustical ceiling, and the lights are below them, and the lights are being reflected by the sails. I thought it was an interesting way of incorporating it inside the building. Now, by the way, I should mention, the 67% energy reduction came back to them from the utility company, and they gave them a rebate that paid for the infrastructure upgrade on this building within 3 years. That's a phenomenal rate of return. Now, it would have paid itself back without that rebate, but it would have taken probably 5 to 6 years is my guess. When they did the math for the LEED, they only found a 54% energy savings. And I say that with Jeff because 54% is still, wow, phenomenal. The potential in the future is hybrids, I think, and water and most likely displacement will play a major part in that. So that leads me into the next product, which is displacement ventilation. The displacement ventilation component is basically supply air that is allowed to distribute itself inside the room, where on an overhead mixing system, we use the energy in the supply air, the velocity, to drag room air and mix it thoroughly. In the case of displacement, the last thing I want is any significant throw distance out of the face. Often, the diffusers are in the same location as occupants. And we typically, as a design rule, say you shouldn't be closer than 3 feet if you're going to be in continual occupancy to the face of that diffuser. But in reality, you can be within 2 inches of it, still not feel the face velocity coming out of that system because we designed for 40 feet per minute. Now, because we're not mixing the space, this allows the cool air to pool on the floor. And as an occupant or a heat load, you naturally reject heat to the air surrounding your surface. And that makes the air warmer, slightly more buoyant, and it moves upward around your body or around the equipment. And that in turn will induce or drag air from a lower level, perhaps this cool air on the floor, up around your body. And it does it in a way that, as an occupant, you're never aware of the air velocity inside the space. It's simply so low, and it's simply because we always have these plumes going around our body. Again, for more information on this topic, I would refer you back to our webinars that are on our website. One note I would make is that this achieves a phenomenal level of thermal comfort. In terms of flexibility, I consider this one of our most flexible ones, even though the face area involved might be fairly large depending upon the space. I can change its shape, its location, its color, how I integrate it inside the building spaces much more readily than I can with overhead mixing systems. Now, the location of this can actually be in the ceiling plane, in a wall, and in a floor. Gravity drives everything, so all that has to happen is the supplier has to be cooler than the occupied space for it to work correctly, and not directly over the top of an occupant in the case you're using the ceiling. Now, this implies correctly that you cannot heat with this effectively, and so oftentimes radiant heating is used either in a slab or from overhead. Because hard air rises, you just can't get a very effective heating with it. It's its flaw. One really cool application that shows probably one of the highest levels of integration that we've been involved in is the Edmonton Airport. Now, this is in numerous cases through the building incorporated into visual parts of the building, such as this flight information board. Now, these diffusers are stainless steel. They have a custom face. You can see that there's this band around the diffusers that is not perforated and actually has the electrical service or the data service or other services attached to the product. It is also curved to match this oval shape. Phenomenal level of comfort comes from this building. Now, in order to get the most effective fit of this product inside this type of structure where you're using it as a part of the structure or the finishing, is to have us be involved from as soon as possible, because we have this whole list of do's and don'ts that we've learned over the years that we're more than willing to share with you in an effort to try to get the most successful job for the least amount of effort possible. And we had that with this job. It just went so smoothly. Another example of a high level of interaction with the architect is the Beth Shalom temple. This originally I was called in to talk to the architect about the possibility of not having anything visible. And for instance, along the glazing, which you can see through the white box perhaps, the radiant heat is convective from flush to the floor. So we have bar linear faces over it and a heater element at the bottom. The supplier, in this case, the interior finish design, selected these wall-mounted diffusers, and they have a very, very large open pattern to them. Now, as a supplier of air movement, I can't really use that large of an opening supplier. So there's most likely 3, perhaps 4 layers of perforation to make the uniform phase velocity happen here. Now, what I really love about this building is the end user went to the engineer and sent them a data file, which they then shared with me, that they started monitoring the temperature in this building in October, I believe it was last year or the year before. And they started at 6 a.m. and they measured the space set point and temperature sensor in the space. And they went from 0 occupants at 6 a.m. to 125% of occupancy at noon. And the temperature inside this space did not vary by more than 1 degree, even though the supplier volume did not radically increase. And this is simply because if you put the cooler on the floor, in essence, you're activating the floor as thermal storage. And you can achieve a great deal of flexibility in terms of surge of occupants in and out of space with minimal, if any noticeable, impact on what the occupants perceive. Now, of course, this is a movement that a lot of designers are moving toward, is to involve structural elements as thermal storage. So this is just a classic example of it. Another example of high level of integration is in a casino. Now, Edgewater was our first casino that we worked on with displacement in it. And in this case, we show it incorporated in the casework, either in this buffet table here or along this, this structural wall dividing this mezzanine level from the lower level, which had slot machines in it. Now, in the slot machine area, it was actually displacement from underfloor diffusers. A really cool incorporation of this product. Now, this was not a smoking structure, but we have many casinos where displacement's been used because I'm stratifying this room. I'm moving all the heat and the contaminants to upper levels, and if you have somebody smoking, that smoke byproduct is typically warm, and you can watch the tendril of smoke from the end of a cigarette float up to the ceiling level. It never dissipates really. Now, there was one casino in Milwaukee that showed a reduction of smoking particulates in the displacement part of the building compared to the mixing part of 50%. Now, I don't know that there's anyone that knows what an acceptable level of smoking byproducts are, and I don't. But I do know that from an occupant's perception, even though they're smoking in close proximity, you're really not aware of the fact they're smoking inside these structures. And casinos, of course, want your money, and they're more than willing to invest in getting it. And if you want to smoke, smoke. If you don't, don't. So it's heavily used in casinos. It's also heavily used in public spaces like this, this library, Elk River Public Library. And this was a LEED Gold product building. Displacement ventilation. You can see it's incorporated in these vertical risers between the book shelves. This is a 180-degree round diffuser with the top part being covered by an acoustical face. So these are top fed. You could have fed these from the bottom or the back. You could have put shelves on them. I've seen them used in common areas of high schools where they're along the edge and they put their trophy cases on the top of them. There's all these different ways to incorporate in the building structure. But one thing you can easily get out of displacement is it's incredibly quiet. Now, in the case of 100% outside air, it's also one of the cleanest air supplies that you can breathe from an occupant's point of view in a building. Now, this is Manitoba Hydro. This uses radiant slab heating. It's far enough north it needs the radiant slab heating this time of year, in fact. But it's 100% outside air. And it's hidden in this black median around the exterior part of the room. This is the displacement service inside the space. Now, first blush, when I look at this, I thought, wow, we hid the diffusers behind the wood flax. And in fact, I spent a lot of time hiding air diffusion products behind wood products, to be honest. And I've recently put chill beams behind wood slats of this type, linear slots, ceiling diffusers. There's a lot of ways of moving air, but in this large of a void, displacement shines because I don't have any need to mix the air above the occupied level. It's a waste of energy to do so. An area that sees a large amount of foot traffic and swings is an airport, and of course also a fairly large solar load, depending on where it's located. In this case, the San Jose Airport uses displacement diffusers. They are located in two places. The first is along the interior wall of this concourse, and these diffusers are incorporated throughout the entire length. They had a custom perforation. They're full height, so they look more like a wall component rather than a discrete product. And then along the exterior where all the glazing is, there are these vertical units originally installed, cylinders with a domed top on them. And we're supplying from two sides in this case because it is a fairly wide space. The typical surface area distance is, our design goal is 30 feet as a radius. So I mean, this is very well handled. Again, a very comfortable place. And we've seen a lot of airports worldwide start using or have been using displacement ventilation. Another example, I guess, actually, is the San Francisco Terminal 2. When they renovated this, they actually found a 20% energy savings in above and beyond what Title 24 required in their buildings using displacement. And you can see in the back corner of this room the displacement diffusers that are integrated here. And they were sized and shaped such that you get this interesting pattern of lines that's actually discrete diffusers. Again, in San Francisco, this music conservatory uses displacement ventilation. Now, if you want to talk about a space that has some challenging acoustical requirements, it's one of these types of spaces. Anywhere I have fine art presentations ongoing, if I'm recommending, I always start with displacement because I can meet NC10 in these spaces from a supplier point of view a lot more readily than I can with anything else. Also because of the variance in occupancy, I can handle the loading far more effectively. And you can see around the stage that these displacement diffusers are installed. Now, one of the things that we had come as a concern from the acoustician on the job was, will these impact the tonal quality of the piano, for instance, or if it's vocal? We did an analysis and did some mock-up concerns and found that it had minimal, if any, impact. So whenever we run into a problem or an area that we have less familiarity with, we always rely on either physical testing in our laboratory spaces or a physical mock-up, and sometimes both. The image you see here is Legacy High School. It's the last displacement job I'm going to discuss, pure displacement. Now this is, I believe, a radiant slab floor again. But you see that in between these windows bays, you have these vertical boxes. Those are actually the displacement diffusers with a perforated face on it. You can see the supplier duct being fed from above. I can tell you right now that these kids have no clue where the air is coming from. Probably never occurred to them to ask. If it was a discomfort area, though, high velocities or noise, they would have known and been able to point to it. So what we find is that people vote with their feet. Anytime I go into a building with displacement, I see people often in very close proximity to displacement diffusers, indicating there's less discomfort and less sound problems. Underfloor. Underfloor air is typically supplied through raised access floor. Although it can be individually ducted, the most economical one is a pressurized funnel. And you can see in the bottom, we have this dashed line drawn across above the occupant's head. This is what we consider our design point, where we try to thoroughly mix or optimally mix in this space to 6 feet above the finished floor. And above this magic line, we start letting the air stratify more thoroughly. And the idea is that I'm not taking any heat from the upper levels back down in the breathing zone, nor am I taking any contaminants back, say the cough from your coworker or the sneeze. One reason that I've seen underfloor used before is that you can incorporate the building surfaces in the floor. And I actually seen several jobs go together weeks to as much as a month faster than what they'd originally estimated, because all of the contractors have full access and they don't have to get in the way of each other like you do sometimes in overhead systems. So in terms of flexibility, the color, again, very high on that list. The location, the integration, the shape, very, very good flexibility there. The one that's somewhat limited is the size of the device. They're in the center part of the building, they're often round 8 or 10-inch devices. There are some on the market that are square, but they're usually a discrete size. Now, when we get into the face aisle, those really have maybe 3 choices. There's not a lot of flexibility there, but when you get to the exterior part where you're washing the windows or the walls for thermal control, we have a lot of faces on bar linear products that make that. And I'm going to show you at least one case study that we can discuss on that. So the first building in this presentation is CalISO headquarters in Sacramento. It's a platinum building. They used underfloor air distribution to the bulk of the building, and in select areas, displacement incorporated in the walls, in conference rooms and other spaces. What they achieved was a 40% more efficient design than what Title 24 called for. And they also achieved individual control of the diffuser volume by phase operation on this unit. A building that's very interesting to me is the J.E. Dunn headquarters. Now, J.E. Dunn is a large general contractor that has a very good track record as a leader in sustainable design. Their own headquarters building, they wanted to optimize it. And they ended up putting underfloor in this wood flooring, and you can see the diffusers located throughout the space. But what the end result was, that they only used 2 watts per square foot for energy consumption inside this building, and that's just a phenomenal goal. Hats off to them. My favorite place to use displacement actually is in churches. And this came from an analysis I did about 12 years ago where we had a historical church. They wanted to renovate, and churches have this typical natural stack built into them, particularly cathedrals, where we have a bell tower that acts as sort of a chimney, and in the traditional European cathedrals you have windows along the perimeter for the pew area, and you would open them up in the summer, the cool air would pour in, and then the heat would rise up and draw more air in. All good and done. But if we were going to mechanically ventilate it, then I have to have diffusers somewhere inside the space. Now, this original mock-up request required us to put the diffusers underneath the pews of the Catholic service area. And this cathedral is actually one as well. And you can see the kneelers, and you can see perhaps the diffusers directly underneath the pews. So you can imagine that if they use the kneeler, their feet are directly on top of these diffusers. So one of the questions that we had to resolve and found quite interesting results on was, will people be aware of the fact their feet are on top of diffusers, particularly women? And I'm not trying to pick on them, but they typically wear more open-toed shoes than the men. And being as there's nothing between them and the diffuser, will they notice? And the answer is some will, but a majority of them will not. Now, in our building goal, of course, is we want at least 80% of the occupants to consider the space thermally comfortable, and we achieve that very readily. Now, the other thing about it is, as I mentioned on the Jewish temple earlier, was the displacement from the sidewalls. This is displacement from floor. I am activating this floor as a thermal storage media, and it works incredibly effectively at that. Another place that used very successful underfloor displacement is the Seattle Public Library. So I look at this example, and I look at this previous example. How do you possibly use overhead air distribution inside these types of structures? It's a challenge that I would find quite invigorating and also enough to make me beat my head on the wall, perhaps. This one in particular, there was a design project competition that I was talking to the instructor on, and he said he had 3 teams or 4 teams that looked at how to condition the space, and they all tried to put overhead diffusers in, and none of them considered displacement. So I kind of look at it in this space and in this space as the traditional school approach would be to mix this void, but there is absolutely no need to do so. And if I cut this down by using stratified systems, I drop my air volume drastically. And I get people in close proximity that are very comfortable here. A classic example of this is the Kaufman Center for Performing Arts. Now, this one has an interesting structural aspect. This curtain wall is curved, and the curvature radius varies as you travel along it. And so each of these linear bar diffusers that you see between these structural elements holding the building up is different radius of curvature, which involved a great deal of integration with us as a manufacturer supplying it and the architect to make certain we had the right products in the right place. Now there are returns incorporated that are these linear slots underneath these openings on the mezzanines. And the engineer at the end of this project sort of flabbergasted. He said, you know, he estimated that we used 1/3 to 1/4 of the air volume in this space that would have been required to do this with overhead mixing. And of course, we had none of the aesthetic challenges that would often be found if you're trying to do mixing in a glass ceiling. It's just an amazing synergy how we were able to incorporate all of these elements inside this space. And then you look at this other room in the Kaufman Center. I love wood. This is wow, okay? But we ended up putting displacement in here as well. Now this had a really stringent acoustical requirement, and one of the best ways to drop the acoustics down to even lower levels is to put in smaller volumes of air. So unfortunately this leads to more diffusers, as you can see underneath these seats on the right hand side of that little insert image. Well, the net effect is a very, very quiet, pleasing space. And again, no reason to air condition a space we don't have occupants. Now we get down to more of the traditional approach where we have overhead systems. And just as a reminder, mixing systems' goal is to thoroughly mix the space. And I have to worry about both heating and cooling in this case because I have hot and cold air. And I need to make sure that I don't throw the air too far in cooling mode or not far enough in heating mode. The differences in distance and throw is due to the buoyancy of the air. And my goal, of course, is that I have occupants that consider themselves thermally comfortable. My goal is to make sure that I have fully mixed the space, I fully cover the space, and I achieve at least 80% thermal comfort. Now, it's a sad indictment of our design approach over the decades since Willis Carrier introduced forced air systems in 1903. Our goal has always been at least 80% of the occupants expressing thermal comfort or satisfaction with their environment. And a recent study by the Center for Built Environment, where they looked at over 100 buildings on the North American continent and I believe a few overseas, they found only 59% on average considered their space thermally comfortable or acceptable. So we're missing the mark. And from my own personal experience as a researcher in human comfort, draft at the head level is a primary driver for this complaint. So in this case, although that's a cool aesthetic on the linear bars on the side, several things come to mind. One is, will I be close enough to feel draft? And the other is, will I move the curtain? So these are things that we look at when we're doing the design. And by the way, in this case, the answer was there's no problem with either of those two items because of volume and velocity. So in terms of flexibility, this actually is probably one of our more flexible products because there are, I estimated in our product line alone, there's over 900 different sizes, shapes, and types of overhead diffusers, roughly. And this leads to a large number of faces, sizes, color shapes, and so forth, and incorporation in floor, wall, ceiling, etc. So one interesting type of air diffusion you see in large bay areas like this commons area is nozzles. They are characterized by really long throws. They're a cool look. They're easily directionable. You know, there's nothing wrong with these devices in here. And actually, in this way, I'm not really mixing the area above those nozzles. I'm actually only mixing the floor to the nozzle level and a little bit above it. So I'm actually, in some ways, stratifying this zone. The only challenge is if I had an escalator going up in close proximity to this, I might find a case where the nozzle is blowing directly on the people on the escalator. And with my my lack of hair, I would probably notice that. But generally, these are used quite successfully. Another very common use of sidewall in an atrium is linears, either bar linear or discrete linear slots. And in this case, for this wood finish, there was a color complementary selection made. And even though this linear is continuous in appearance, my guess is only parts of it are actually supplied. Some of it actually could be returned. So we can blend this in a way that gives you the continual line appearance, which I've been told is often desirable, and yet still gets function and performance. One interesting room, again, is back to my conference room, this curved linear slot. Now, it's my understanding this is the first curved linear that Jerry Price's company manufactured, and they wanted to highlight it by putting in this curved soffit. So this is an in-plane curvature, but we've actually done convex, concave, or complex curves. There was a church structure in Southern California that had a domed, an egg-shaped dome, and we had a complex curve in there and a linear line all the way around the interior. And it's my understanding they went together on the first try. That's a successful blend of manufacturer integration with contractor, integration with architect. You don't want to do these twice. Another classic example of linear lines being used to supply and return are these linears chasing the perimeter of these varying recesses in your ceiling plane. And one of the last types that I will show is sidewall linears. Now these are often bars in this type of case, or it could be a sidewall grill. Color, shape, mostly length or height are the primary considerations here. But when you get into a space like this, you might have multiple types of these products involved. You can see in the case around the perimeter of the balcony area that this is a continual line, but underneath the balcony here you have a return that's maybe a different type of linear. You know, the sad truth is I could talk about this type of stuff probably all day long, and we don't have time for that. So perhaps we should summarize. And I look at air movement is actually an art in many ways, not unlike interior finishes. We want to make sure we pick the proper product for the owner to meet his requirements, be it a more energy efficient space, a cleaner air space, or just simply a high level of thermal comfort. There are a lot of opportunities out there, and as long as we're involved early in the process, along with the basic design, we can give a lot of suggestions that may make the planning easier for you in the long run. And as I mentioned before, we have a lot of do's and don'ts that we've learned over the years. We call that paying our tuition, if you will. Now, one way that I often can help you settle on a design, and also your end user a lot, is a mock-up. This image shows a mock-up that we have currently installed in our lab in Atlanta for a hospital room that's using chilled beams. Now, this is the four-way discharge beam, and you can see a little bit of the theatrical smoke and supply air in this image. This wall is hot or cold is based on the wall requirements of the building structure. We go to the level of putting up the walls dimensionally, the diffusers, their volume, in this case water supply. Everything is closely matched the requirements of the job so that when you come and visit it, you can actually, in essence, in many ways, be in that room before it's actually built from an air performance point of view. And yes, in case you're curious, we can take the mannequin off the bed, which is, by the way, the mannequin's heated. We can put you down instead and take a photo of you with theatrical smoke around your body. So it's sort of proof you were here. It's kind of surprising how many people actually want that photo. Kind of cool, too. Again, we want to balance form and function. And together, we can have a very successful synergy and a very, very well-received structure when we're finished.
Thank you very much, Jerry. We're going to go ahead and open up the floor for questions now. You have a little question section on your GoToWebinar toolbar. So if you'd just like to type those in, we can go ahead and start addressing those for you. I have received a couple of questions already. One of them pertains to the mock-ups and that kind of thing. You know, when you're looking at some of these custom applications, or these, you know, say take the displacement diffusers with the customized shapes and so on, how often are mock-ups and that kind of thing required? Is it, you know, if you're working with these technologies, is it just, you know, 10% of projects that have heavy customizations? Is it 50%? What's the degree?
Well, first off, I should start off, there's several levels to mock-ups. One of the most common requests doesn't actually involve much on your side. Is will this shape perform correctly? We call that a laboratory mock-up, performance related indices, and we do those a lot for displacement in particular because it's more commonly customized, and actually increasingly for chilled beams as well. So how often is it? Most buildings don't require a full-blown mock-up. It's when you get on the cutting edge or near that cutting edge, like that chilled beam inside a patient room example I just gave you, that we want to assure ourselves that we have achieved a proper design for thermal comfort. And we were one of the people that were stressing we wanted to do this mock-up. I'll be honest with you, I was going to do this mock-up whether the end user wanted to or not. Okay, just simply because I always learn something from these mock-ups, and I love the interaction between you and me. It's always a learning experience.
Thank you, Jerry. you know, color rated very highly as, you know, having a high degree of customization. What does that mean? Does that mean white and stainless steel, or does that mean hot pink?
You know, it's an interesting question. This is not Henry Ford, where you can have any color you want as long as it's black. Although, ironically, black is one of our standard colors. We do have standard colors of white, black, gray, which is sort of fall aluminum finish, and then we have clear coat, anodized colors, and so forth. But when I mean colors customization aspect is high, it means that if you give me the Pantone color code and an extra week or two of lead time, it'll come out with that color. And it's powder coat, what we do primarily. So it's going to be a very durable finish that will hold up to a high level of corrosion and user abuse from, you know, either rubbing or other things. There is an incremental cost associated with a color change, but it's minor compared to the benefit you get for incorporation.
Thank you. What technologies tend to be best suited for retrofit applications?
You know, that's interesting in a way. One of the first questions I would ask if somebody came to me and said, I want to have a renovation of a building, is where is it geographically located? My background is in human comfort and to a great deal building performance, envelope performance in humid climates. And when you start talking about historical buildings, often the environment is one of the deciding factors. Let's go to, well, let's just pick Atlanta. If I have a building built 30 to 40 years ago, there is most likely not a significant vapor barrier, or if there is a vapor barrier at all. Buildings built in that era and earlier often had a large amount of natural infiltration through them, sometimes as much as 30 air changes, more commonly perhaps 20. In today's buildings, we have about 6 to 4. So we've trapped the moisture, we've kept it from migrating through. So if I'm looking at the two technologies that I've stressed a lot on, chill beams or displacement probably would be a little more at the front in the building if we're not going to change the envelope and put in a vapor barrier. Or we're not going to do some sort of pressure control for vapor. You know, it's not something I can give you a general guidance on, but the one that should fit almost every environment is displacement. Overhead mixing, obviously. Chill beams can and have been used in very, very humid climates to the very dry, but it's all about the controls, the envelope, and how we're approaching the design.
Thank you. The last question we have time for today, who typically drives the selection of technologies or drives the identifying the opportunity for these kinds of technologies in a scenario where you're trying to break away from the overhead?
I've seen both architectural firms driving this technology change. I've seen engineering firms driving this change, and I've actually seen owners driving this change. So in terms of who is the most common, the owner is not the most common, honestly. Although some of the major projects are really driven by the owner more than the architect or the engineer. We saw a lot of change in the approach of building designs in the last 10 years, in no small part because energy codes have become more restrictive. We need to save or consume less energy as time goes by, and that tends to move away from some of the traditional designs. So as we start approaching that goal of 100% energy reduction compared to the base building model of ASHRAE 90.1, you're going to start seeing more and more products considered automatically like displacement or chill beams or those type of things, simply because the energy savings offered.
Thank you. Well, thank you very much, Jerry, for your presentation today. Thank you for everybody who has joined us for the last hour. Up on your screen, you should be able to see our next upcoming webinar that will allow you to earn an AIA credit, and that's coming up in February, High Performance Design Through Service Integration. In the meantime, you can expect an email from us in about 20 or 30 minutes that will receive a link to the short AIA credit request form. So if you could go ahead and follow that link and complete the short form, we can turn that credit back around to you. Thanks again for joining us today, and enjoy the rest of your afternoon. That concludes